about electronics, you probably imagine hard, rigid structures like this mobile phone. But John Rogers from the University of Illinois is working on soft and stretchy tissue-like devices that could actually be integrated with the human body. We haven't got that far just yet, but to see if it works, John's team has already implanted an array of LEDs under the skin of a mouse. I'm here at the MRS Fall meeting in Boston to talk more about this research with John.
Hi.
Your Symposium X presentation here at MRS argued that semiconductor technologies that bridge the gap in form and mechanics will create new opportunities in biomedicine. It sounds intriguing. Could you elaborate more on that vision?
Yeah, it's a direction of research that's really motivated by an observation that all known forms of biology are soft, elastic, and curvilinear, whereas all known forms of electronic technologies are rigid, planar, and brittle. And as a result, if you want to integrate electronics with biology, with human skin or tissue, you have severe challenges in a mechanics mismatch and a geometrical form mismatch. And so because you can't change the biology, we as material scientists have focused on new ways to use semiconductor materials in electronic devices that have the shape and the mechanical properties that match those of human tissue to allow an intimate mode of integration that can be useful all the way from advanced surgical devices to implantable monitors and therapeutic systems.
These LED arrays you've put inside a mouse, what exactly were you trying to show by doing that?
Well, we're trying to show that we can structure electronics in formats that are much more tissue-like in their geometry and their mechanical properties compared to conventional devices that are built on the brittle, plain or rigid surfaces of semiconductor wafers. And as part of that work, we got interested in light-emitting devices for several reasons in the context of biointegrated systems. First of all, there are spectroscopies or ways that you can diagnose tissue based on the way that they reflect and absorb light. So you can determine the state of health of different tissues. Another reason why we're interested in light-emitting devices in the body is that there are certain classes of drugs that can be photoactivated. So you introduce them into the body in an inactive form, and then you can activate them locally by exposing them to light. So that's another reason why light in tissue could be important. And the third one is that there is an emerging set of research results that indicates that phototherapy can actually accelerate the wound healing process. So for those three reasons, we think there is value in being able to integrate light-emitting devices either on the surface of the skin or internal to the body on tissues of organs and so on.
I've seen photos where you've put tiny LEDs onto the end of surgical gloves. What were those for exactly?
So we're generally interested in types of devices that can be integrated with surgical tools to improve the efficacy of procedures that are conducted by surgeons. And one idea is to instrument surgical gloves with devices that allow the surgeon to locally probe the state of tissue during an operation. And LEDs provide one kind of functionality that might be useful for that kind of process. But also integrated sensors and processing electronics represent other classes of technologies that could be integrated with the glove as well. So LEDs in the context of the surgical glove for doing local spectroscopy of tissue, photoactivated drug activation, or inducing some kind of photo-based therapy.
Another big story is your collaboration with Northwestern University, where you print electronics on clothes and plastic.
Yeah, so that work had to do with a part of the processing sequence that we use to make these kind of biointegrated devices. So the reason why all conventional electronics are built on semiconductor wafers and not directly on rubber, for example, for the kinds of devices that we're envisioning, is that the semiconductor wafer is a very good substrate for supporting the kinds of high temperature processing steps that are needed to build semiconductor devices. And the printing process that we use allows those devices to be built on the wafer and then subsequently lifted off of the wafer in very thin formats and then printed down onto a rubber substrate where we actually build our device. And the process for moving the devices from the wafer to the rubber involves a stamp, much like a stamp that's used to print conventional inks, but designed to print devices. And in that kind of process, the key challenge is how do you control the degree of adhesion of the devices to the stamp. You need them to stick well enough on the stamp so you can lift them off of the semiconductor wafer where you build them, but you don't want them to stick too strongly to the stamp because they need to come off onto the target rubber substrate where you're going to build your device.
I seem to remember a connection with geckos.
So the gecko is a biological organism that offers really exceptional degrees of adhesion on the foot pads of the gecko. It allows them to walk on the ceiling, for example. But it's also switchable because they can pick their feet up when they want to move. And so it's a biologically inspired type of design that we've implemented in these stamps that takes inspiration from organisms like geckos and aphid-based insects that accomplish this kind of switching for mobility and adhesion to different surfaces.
Okay, John, thanks for your time.
You're welcome. Yeah.